Okay, we are recording and it's over to you, Emil.
All right, thank you for the invitation to come and give a talk at my old stomping grounds. It seems like I see more people within the era of COVID and Zoom. I see more people that are far away than I see people locally. It'll be nice to have that reversed again in the near future. But for the moment, I'm here to give a talk. I'm here. I'm planning to give a kind of a review of the status of the fuzzball program and what's maybe a little bit of an idiosyncratic perspective on what it is, what it's about, and what to expect from it. Let's see, let me get my laser pointer going. Okay, good. So let me begin by just sort of setting the stage that we've been pursuing an understanding of black holes and their quantum properties for 45 years or more, back to the original work of Bekenstein and Hawking in the 70s. And you know, what was the outcome from that era was that if you make a black hole by throwing in some matter, that whatever threw in and formed the matter is causally disconnected from the pair creation processes that make Hawking radiation. And so it seems like you can't have causality, having the information about what made the black hole be emitted in the Hawking radiation. So locality needs to be violated, locality needs to be violated, or unitarity needs to be violated. And of course, Hawking famously concluded that unitarity was broken, but I think in the era of string theory, we've come to believe that that's not the right answer. And so what we need is some structure which can store the information and then release it unitarily in the later stages of black hole evaporation. You know, the first steps towards a resolution of that puzzle came with calculations in the 90s of, you know, that accounted for a black hole's worth of entropy of near-extremal supersymmetric black holes. So that original example was due to, you know, landmark work of Strominger and Vafa, who looked at a particular situation in string theory where the black holes were charged and extremal and supersymmetric, carrying the charges of D1 frames, D5 branes, and momentum in string theory, compactified to 5 dimensions on a torus, will separate out the circle on which the strings and the momentum lie as a particular circle S1 parameterized by a coordinate Y, and then a remaining T4, which is also wrapped by the 5 brane. And they found that the entropy is given by the product of the brane charges. But that calculation is kind of a bait and switch. Namely, you you enumerate the bound states at weak coupling, and then you claim that it looks like a black hole at strong coupling. Supersymmetry non-renormalization theorems guarantee us that the state count remains unchanged as you dial the coupling. Now, the crossover between weak and strong coupling is something known as the correspondence transition, first laid out by Horowitz and Polchinski. And if you approach, so basically something looks like a bound state of branes at weak coupling, and at strong coupling, it looks like geometry. And coming at the transition from the geometry side, the transition point is where the horizon curvature, the curvature is a string scale at the horizon. So we can ask the question then, what becomes of the bound state structure as we make this transition into the strongly coupled regime? Because ordinary matter, anything that we know of that has a sensible stress energy tensor, is going to obey various energy bounds which force it to fall into the singularity and lead to the information paradox. So, but in various situations, brain matter is not ordinary matter, and we might hope that there's some remnant of the structure at the horizon that can be used to store the memories of what fell in to make the black hole. And so, so the fuzzball proposal, which I suppose goes back to papers of Lunin and Matur in the early 2000s, is a proposal that the strongly coupled brain bound states have some kind of microscopic structure that extends out to the horizon scale. And if that were true, then we'd have a natural conceptual structure for what resolves the black hole information puzzle, because if there's some, piece of parts of the memory of the original infall that are in structures that extend out to the horizon, then you can have causal emission from the horizon scale as you have radiation from a star. Now, that original proposal was in the context of extremal and supersymmetric black holes, but very soon after the original calculation of Strominger and Waffe, there was a very nice calculation of result of Horowitz, Maldacen, and Strominger, that there was an interpretation of the gravitational solution for non-extremal black holes carrying the same charges, which could be written could be interpreted as having bound states of branes and anti-branes. Now, an anti-brane in this context is just a brane having the opposite orientation in space. And if we allow them to interact, they'll start joining and splitting. So the general object would be expected to be some kind of complicated thermally excited bound state of branes. And if you take such a bound state and you extremize the free energy, keeping conserved quantities fixed, then you arrive at a formula like this.
If she's still out biking, yes. If not, she'll do it.
Is there a question? Okay. So, well, that's a little bit mysterious for the generic non-extremal bound state. If we back off a bit and ask, near extremality, we just turn on one kind of charge, anti-charge, non-extremality, then we're very familiar with what arises, for instance, if we take a particular scaling regime to take the circle along which the strings are wound to be large relative to the remaining compactification, then this leads to, at low energies, an ADS3 scaling regime in the geometry. And this formula for the entropy is just the standard asymptotic density of states of a conformal field theory. Turning on yet another kind of non-extremality, say the one branes and anti-one branes, one can interpret the resulting entropy formula as a Hagedorn entropy of a string that's living bound within the 5 brane, known as a little string. And so keeping the 5 branes extremal, but allowing the general non-extremality of the other 2 charges leads to what you might consider as the Hagedorn entropy of the little strings. And this regime is of interest as a kind of a bridge between ADS asymptotics and flat space, because conformal infinity for the decoupled 5 brane theory is null. It has much more the Penrose diagram looking like flat space than the Penrose diagram of ADS, where the boundary is time-like. And now, having that sort of non-extremal 5 brane dynamics in hand, if we did, then we could think of the ADS3 regime as a particular low energy limit of that more general object of the non-extremal 5 brane. And this is a viewpoint that we'll take in the rest of the talk. And one of the conclusions that we'll draw is that what's happening when we approach the threshold of black hole formation, even in the ADS3 limit, is intimately bound up with the sort of little string theory dynamics that is true more generally at larger non-extremality. Now, we can consider these various, we can focus or isolate these various regimes of behavior by either tuning the energy of the bound state, the size and shape of the torus, and the string coupling constant. So for instance, this ADS3 CFT2 scaling regime that we looked at in the last slide is a limit where we take the energy to 0 and this special circle to be large relative to the others. Similarly, the non-extremal fine-grained limit is one where we take the volume of the torus to be appreciably larger than the string scale, so that the five-brains are much, so that's a torus that's wrapped by the five-brains, but not by the strings. And so by making that large relative to the string scale, we make the five-brains parametrically much more massive than the strings. And so the low energy limit is dominated by the non-extremal one brains and not the non-extremal five brains. We'll also be, in fact, for much of the rest of the talk, we'll be looking at not the original duality frame considered by Strominger and Valfa, but the strong coupling dual of that frame where the background charges are Nivas-Schwarz five brains and the strings are fundamental strings instead of D strings. And this has the advantage that just in energetic terms, the Nivas-Schwarz five brain tension goes like 1 over G string squared as opposed to 1 over G string for a D brain. And that makes it a solitonic object in supergravity. It's like, you know, a monopole in Yang-Mills theory is a semi-classical object. And so much of its structure will be revealed by thinking about semi-classical closed string dynamics. It also has the advantage that we can study it in perturbative string theory. So, studying backgrounds with Ramon flux turned on is a notoriously difficult issue in perturbative string theory. The technology for dealing with Ramon flux in worldsheet string theory is almost undeveloped since its inception. And so by allowing yourself to consider objects, bound states of objects which only source NS flux, we can sidestep that issue and still make some progress. Now, this question of where you are in the moduli space of the background torus and the string coupling affects which of these two duality frames, the D brain frame or the NS frame, is appropriate. And so I've indicated here that what you might call the 6-dimensional string coupling, which is the string coupling scaled by the volume of the torus, ranges from 1 because of some strong weak coupling duality in this parameter out to infinity. And as you dial it up, that coupling up, as you dial it down from 1, initially the appropriate low energy supergravity frame is the NS frame. Then past some point, which is governed by the charge quanta, it passes over to a low energy description where the D1, D5 frame is appropriate. And then at some point, a perturbative gauge theory approximation holds. And that crossover is what before I was calling the correspondence transition. So in particular, if the number of five brains is and one brains is approximately equal, then virtually all of the range of couplings is governed by the D brain frame. But if you're interested in a situation where, say, the number of five brains is moderate and fixed, and the number of one branes is asymptotically large, then virtually all of this range is governed by the NS frame. And so in particular, if you're wanting to think about the limit of, say, one 5-brane and a bunch of fundamental strings, then the NS frame is appropriate for that. And I think you guys heard a recent talk, maybe last summer, from either Gabardil or Gopakumar and Eberhardt, who have been exploring world sheet description of that situation.
Sorry, Emil, can I ask a naive question?
Yeah.
I remember from student days that down the throat of an NS5 brane, the string coupling constant tends to grow, and so the CFT description becomes suspicious. Is this closer than you want to be, or is there, for some reason with the other ingredients, it becomes a fixed scalar in the NS frame, or?
Right. So what's happening is that of these two parameters, the volume of the torus and this G6, one is a true modulus and the other is a fixed scalar. So if we're in the NS frame, it's the volume of a torus in a perturbative string description is a completely free modulus, and so it's V4 is the modulus and G6 is the fixed scalar, which is determined by the ratio of the charges. If you're in the other frame, it's exactly the reverse. It's the V4 is the fixed scalar and G6 is the modulus. So, sort of pick your poison. Basically what's happening is that if you're say if you're in the D1, D5 frame where the V4 is the V4 is the fixed scalar, then as you start trying to dial the G6, you're dialing the string coupling. And so you reach some point here where if you just look energetically at the cost of a D string versus a fundamental string, say wrapping some cycle of the T4, you find that they exchange dominance at this point because of the fixed scalar condition. So that's a calculation that was done by me and Finn Larson back in the early 2000s. So
the upshot is that you can control both G6 and G10 in a way that makes you confident of what you're saying in the NS5 picture?
I think what I'm saying is that G6 is always below 1 for my purposes, and that G10 becomes of order 1 at this point.
Okay.
And so there's some duality, which is like S duality times T duality on all 4 cycles of T4 times an S duality back again. And that duality map changes G6 to 1 over G6. So that's why I've indicated that only the G6 bigger than, less than 1 is a fundamental domain of the moduli space. But then furthermore, if at some point, G10 becomes bigger than 1, then you should do an S duality transformation. And so that's what's happening here. Okay. So as a first warm up to, what sorts of stringy things await us near the horizon, we can think about just having non-extremal 5 branes. And so the geometry in the radial time plane has long been known in world-sheet string theory to be described by a gauged Western-Witten model, where you look at a non-compact Western-Witten model on the group SL2R, and you gauge the time-like U1 translations. And so that leads to an effective geometry, which is somewhat cigar-like. Asymptotically, it's a circle of fixed radius, which is related to the Hagedorn temperature of the little strings living in the 5 brane. But it was noticed, but this Western-Witten model exhibits a phenomenon which is called Fatayev-Zamolodchikov-Zamolodchical, or FZZ duality, in which this cigar geometry comes along with a expectation value for a certain winding string condensate, whose coefficient is related to the parameter in the geometry which determines the string coupling at the Euclidean horizon. And so it's not like there's some string matter and then it's coupled to gravity. It's more like if you were to try to wiggle the geometry, you wiggle both the geometry and this condensate at the same time in some correlated way. So it's not like you can separate one from the other. And so the question, so this is an indicator that there is some stringy physics that is going on at the Euclidean horizon. Now, at the horizon of the black hole. The question of what the interpretation of this in Lorentz signature, I think, is open to debate. There have been some articles in the last, some work in the last 5 years or so by Givon and Itzhaki, who've been trying to argue that it implies that the interior of the black hole is filled with highly excited strings, which might be an indicator of this sort of idea of the brane bound state structure extending out to the horizon. On the other hand, it might just be that you could say that the physics at fixed Euclidean radius translates in the analytic continuation to Lorentz signature to the physics of a uniformly accelerated observer at fixed radius. And if you get close enough to the horizon, the uniformly accelerated observer reaches the string scale acceleration, and equilibrium has to be in equilibrium with the Hagedorn gas of strings. So it's not completely clear what this, how to interpret this, but cousins of this FZZ duality will make an appearance later in the talk. Okay. So the next step in the story is to start introducing the fuzzballs as they were originally introduced by Lunin and Matur. And so the idea here is you might say, okay, I can't maybe understand the general structure of black holes through in string theory, but let me try to understand the story, near extremality, where Strominger and Waffe could do their count, and with enough supersymmetry that I have control over the calculations. And so, so one way of thinking about this is to say, okay, well, let me start not with all three of the charges in the bound state, but with just two of them. And indeed, the configurations of two charge bound states have been completely enumerated in these two works. And so these are things which they're not quite black holes. They're sort of on the boundary of a regime of the phase diagram in energy and angular momentum in the transfer space. They're sort of on the boundary of the phase diagram, where ordinary ADS3 black holes are the gray shaded region. But you see that they sort of come in towards one another. So if you move in to lower and lower angular momentum, you start to approach the extremal BTZ black hole. So they might be useful in that sense. There's been some controversy in the literature as to whether you should regard these two charged things as being like small black holes. My attitude is that you're in the correspondence regime, where the horizon is smaller than the string scale, or at least at string scale. And so you're basically in this correspondence limit where you shouldn't trust geometry anyway. So let's first consider the two charges to be the 5-brane charge and the momentum. And here we have a completely geometrical understanding of what's going on. So in particular, the fields that live on the 5-brane.
Sorry, Emil, can I ask a question about your previous phase diagram?
Sure.
What's the dark blue region or the purple region?
The purple region is what the system, so in the light blue region, is the regime where the system has so much angular momentum, the horizon wants to be not a sphere, but a torus. And so the geometry of the black object here is a black ring.
Mhm.
As you come into smaller angular momentum, then this work here showed that what the system likes to do is a division of labor, that the blackness is carried by an ordinary 5-dimensional black hole with a spherical horizon with a ring around it of something called a supertube, which is a 2-charge object which basically is there to carry the angular momentum, but has no horizon structure.
Okay. Okay, thanks.
Okay, so let's look at these NS5P supertubes. These are 5 branes basically with a gas of chiral waves on the brane, with all the momentum along some particular direction, which will be this Y circle. It'll be the T-dual of the circle we're eventually interested in, but let's start here. So among the degrees of freedom on the 5 brane are the scalars which parameterize where it is in its transfer space. And so we can have some kind of general superposition of waves on the brane where the momentum is all along the Y circle. And we're going to implement some sort of twisted boundary condition that winds all the 5 branes together into a single 5 brane that's wrapping this Y circle n 5 times. So all the 5 branes then are bound together by the twisted boundary condition, and the momentum is bound to the 5 branes, and the 5 branes are just executing some kind of wiggly shape, which I've indicated here, drawing just 2 of the 4 transverse dimensions to the 5 brane. And the color coding evolves around the color wheel, indicating this twisted boundary condition. So we can count all of these states. There are basically 8 bosonic and 8 fermionic polarizations. As I said, the bosons include these scalars describing the transverse location of the 5 brane. And so in some enumeration of the states, we can say how many modes we have excited with a particular wave number and particular polarization, count all those things up with the boundary, with the overall boundary condition that the total momentum is N1 and N5 NP. And that counting problem then leads to a 2-charge entropy, which looks like the 3-charge entropy where I've just thrown away one of the 3 charges. So this entropy is, of course, macroscopic, but it's sort of subgeometric in the sense that if you ask what's the horizon area of the geometry sourced by such a collection of branes, it's a string scalar smaller. And so we shouldn't trust it near the source. Now, we can then, having those solutions in hand, and I'll describe them, the metric and other fields in a moment, we can use the standard rules of T-duality to convert it into an NS5 F1 solution in a near horizon ADS3. And the process of making that T-duality, well, if you just look at the wiggly 5 brane, it's sort of partly along the circle you're trying to T-dualize, which is V or Y tilde, and partly transverse. And so there's some mixing that goes on under the T-duality. The component of the 5 brane that's along the circle being T-dualized just stays a 5 brane, and type 2A goes to type 2B. The component of the 5 brane charge that's locally transverse T-dualizes to a Kaluza-Klein monopole. And a Kaluza-Klein monopole is a solution of supergravity which is completely non-singular. And so what you find after the T-duality is a geometry where there's some kind of wiggly KK monopole core which extends along some one-dimensional contour, but the full space-time geometry is completely smooth. And so this is sort of, a slightly more sophisticated example of the usual mantra of ADS-CFT, where the geometry is not singular and the branes have somehow become flux. So here's the geometry. you can specify the metric, the B field, the dilaton, all in terms of a collection of harmonic forms and functions. And so, and where each one is specified by a sort of a Green's function integral where basically the 5-brane harmonic function. So Z5 is a harmonic function associated to the 5-brane source. So the 5-brane charge density is locally constant along this wiggly contour. And this is just the harmonic function that it locally sources along the contour in 4 transverse dimensions. Similarly, if we were back in the NS5P frame, this would just be the stress energy of a momentum wave along the contour. And so we're just integrating up, a Green's function with that source to create a momentum harmonic function, which then T-dualizes to a 1-brane harmonic function. And so, okay, so we can write down every time you hand me a different profile, I hand you a different geometry. And so this is a realization, if this fuzzball program, that there isn't quite what I would call a horizon yet, but there's structure. And there's different structure for every such source. And another thing to note is that the nonlinear sigma model on this background has enough symmetry in terms of supersymmetry and killing vectors that you can use results of Horowitz and Zeitlin to argue that the sigma model is exact in this background, even if you can't solve it. Now, going back to this phase diagram, which profiles correspond to where you are along this red line of 2-charge solutions. Basically, if you think about it for a minute, I have this wiggly profile, and if I sit somewhere in the middle of it, but away from the source, then the more compact I make the wiggly profile, the more and more peaked the Green's function is. And so the larger the harmonic function Z1 will be, and therefore the smaller the component of GTT in the metric. So more compact profiles make deeper and deeper redshifts in the geometry. And naively, J squared equals 0, so the sort of radius of gyration going to 0 leads to infinite redshift, and that's where you touch, if you like, the extremal black hole point. And so a major challenge is to understand what then implements an infrared cutoff in the system to render the entropy count sensible. And that's something that's still not quite understood. What's understood is you can make the angular momentum squared order 1 or order a few, and so get extremely close to the black hole threshold. And the question we'll be interested in understanding is, okay, as we start approaching the black hole threshold, what sorts of stringy ingredients turn on that will become the things responsible for black hole entropy? And
No, sorry.
Yes,
I was super naive. Just why did you go from the NS5P picture to the NS5F1? What was better about this? You did the counting first in the NS5P picture, right?
Yes.
And then what was better about this second description?
Oh, because this now the NS5F1 description is where you can take now an ADS3 decoupling limit.
Okay.
So these now have an interpretation within the context of ADS3 CFT2. And so all of these solutions, you can, in fact, I've already taken the limit here where I've dropped the constant from both this and this harmonic function. So these solutions have been written in the ADS3 decoupling limit. If you wanted to, go back to the 5-brane limit, you would put a 1 back in this harmonic function, but keep this one as it is. But
and one other very naive question.
Yeah.
Do we have to, in discussing which duality frames are applicable, is that a once and for all question, or does it depend on where we are in the space-time?
it can depend on where you are in the space-time, because so for instance, well, let's see. Actually, no, and let's see. In the ADS3 limit, I don't think it matters. If I just took the 5-brane decoupling limit, then I do have to worry that say in the NS5 frame, there's a linear dilaton, and I could worry that the string coupling gets too big as the dilaton runs into the core of the geometry. So in the NS5 F1 frame, you pretty much, especially if you're trying to think about perturbative string theory, you're in the regime where the 5-brane charge is fixed and maybe large, but the F1 charge is sort of asymptotically large. So that as you're sort of coming down the 5-brane throat and the string coupling is getting bigger and bigger, you want to get to a place where the F1 charge comes in and stops the running of the dilaton before you get to a strong coupling region. And so that requires the number of strings to be of order 1/g string squared in order to effectively stop the running of the string coupling before you reach some place where perturbative string theory craps out. So whenever you are going to use something like this geometry to say something about perturbative string theory, in the back of your mind, you're in this regime where the 5-brane charge is fixed, and the F1 charge is sort of 1/g string squared. So for all intents and purposes, practically infinite.
Okay, thank you.
Okay. So all of that was, I could have given that part of the talk, 15 years ago, and bringing things more to the modern age. People have started asking, already for a while, what happens when you try to add the 3rd charge to this situation? And so the sort of status report is that, yes, you can find 3-charge BPS solutions in your favorite effective supergravity theory that have the same property, that the geometry sort of caps off at large but finite redshift before one reaches a horizon in a way that's very similar to the 2-charge solutions. And the way they're constructed is you start with a particular supertube geometry, say NS5 F1 or D1 D5, and then one sort of plops a momentum wave, a supergravity momentum wave, down in the cap of the geometry in a way that preserves the BPS property. And you try to then construct the harmonic functions that correspond to the generalization of the supergravity solution, and check that the introduction of this additional source hasn't introduced any additional singularities in the geometry. And so a large, once again, a large collection of such geometries have been found, and a conjectural accounting of them using sort of known techniques, sort of extended in believable ways, leads to an entropy which is not quite the extremal BTZ entropy, but falls short by not having enough different kinds of momentum wave you can put into the cap of the geometry. I should say, the structure of these geometries looks very much like extremal BTZ for a large part of the spacetime, namely that there's a parameter A in the geometry which codes the S3 angular momentum. Like in the 2-charge solutions, it's basically the radius of gyration of some supertube profile. and then another parameter B, which codes the ADS3 angular momentum. And so if you work in a regime where B is much, so roughly speaking, this is the momentum charge radius, and this is the angular momentum charge radius. And so if you work in a regime where the ADS3 angular momentum is big and the S3 angular momentum is small, then you can generate a very large ADS2 throat, which, if this were a BTZ solution, that throat would be an extremal throat, which would extend all the way to infinite redshift. But here, because we've carefully tuned things in these harmonic functions, the geometry caps off in some smooth way before you get to a horizon. So these aren't all the states that you would count in the elliptic genus, but they are a large collection of states, and so we could ask what they're good for.
Sorry, Emil, is this NP being represented here by this blue strip? Is that the idea that they're, okay.
That's right. So it's some wave that you put in the supergravity solution, which is running out around the azimuthal direction of ADS3. And the back reaction of that momentum wave creates this ADS2 throat. The sort of supertube solution that this is built on just has some well in it that stops at a finite redshift, but the geometry very quickly outside the source becomes ADS3. And so it's the additional momentum wave that creates this sort of ADS2 regime. And
in this picture, you're trying to show that if it was just a black hole, it would have gone all the way to the gray disk.
Yes.
But now it stops at the black line.
That's right.
Okay, thanks.
So as I said, the strategy is to start with the two-charge solution, a two-charge solution, and then add some additional harmonic function that carries the momentum as some dv squared term in the metric, and then to try to solve the BPS supergravity equations with this additional source. And as I say, the residues of the poles in these harmonic functions are delicately tuned to engineer the smoothness and the finiteness of the capping off of the geometry. So I don't want to go into this because I'm kind of running short on time, but basically there's you can put the BPS equations in some kind of hierarchy such that at every step in the hierarchy, you're always solving linear equations, a linear harmonic function equation for some unknown with some source. And the most complicated is the last step, where the harmonic functions that are remaining to be determined have sources which are quadratic in the previous set of harmonic functions you determined at the previous step. And that's where all of the delicate fine tuning comes in. That you have to make sure that the pole in this harmonic function times the pole in this harmonic function doesn't create some new pole which wrecks the non-singularity of the solution. All right. It's also been determined what the CFT dual is to what you're doing. Namely, the two charge states, as I described them before, are some can be characterized by some labeling of modes on the 5-brane. And for the ones that have, for the 3-charge solutions that have been studied, one starts with a 2-charge solution of this form. Some transverse angular, some modes which carry transverse angular momentum, and some other modes which carry no transverse angular momentum. And then one applies various Virasoro, super Virasoro raising operators to just this kind of mode. And the solutions that have been found in supergravity have been determined to be, in a very precise way, dual to these solutions, which, if you want to think about them that way, you could think about them in, say, the symmetric product orbifold, which is not a CFT in the supergravity regime. It's a CFT which is well inside the correspondence regime. It's the weakly coupled CFT. But because this is BPS, you can track states across the moduli space from weak to strong coupling and determine that the supergravity solution you're looking at, if you track it across the moduli space, becomes this particular BPS state in the weakly coupled CFT. And I should say also that the supergravity solutions are not quite this state. They're sort of coherent states built on this state where you take superpositions with some weighting parameter, some coherent state weighting parameter, where the parameters in the geometry then are the expectation values of the coherent state parameters. Okay. So the supergravity solutions that have been found are smooth. They can have parametrically large redshifts to the cap in the geometry. They approach the BTZ black hole as you take the angular momentum that's capping the geometry off to be smaller and smaller. And with each of these have an identified state in the CFT dual that's counted by the elliptic genus. And so since this original work, the results have been extended in various directions. The holographic dictionary, correlators of like 1-point functions of probes, so heavy, light correlation functions, geometry duals with additional excitations in the global supervirasoro algebra. There's been a nice parametrization of what you're doing in terms of holomorphic excitations, which is expected will in the future simplify the construction. And while I've indicated, a single state where you just have a single of these modes excited macroscopically, and each mode then excited with a particular L-1 excitation of a very particular sort, all in a very coherent way. The multi-mode generalization of this bit of the geometry has been understood. So the idea that you can make this wave much more general has been achieved to some limited extent. And then there's also some work on understanding out-of-time order correlation functions in these geometries. I wanted to talk about one particular probe of this these backgrounds, which has been a subject of study by the Seclay group, which is to look at the 2-point function in some sort of WKB limit, which is basically sending down some wave into the cap of the geometry and asking, what happens to it. And so, so in a sort of a WKB regime, it looks for an awfully long time. If you plot what happens in the in the microstate geometry that I just wrote, you can arrange for, well, the particular microstate geometry I just wrote actually has in the geometry lots of killing vectors. And so the wave equation turns out to be separable. And so you can completely solve in a WKB limit for the wave solution and calculate the 2-point function. And it looks for all the world like what you would see in a BTZ geometry with some quasi-normal mode ring down that persists for an awfully long time. But then, of course, the wave hits the cap in the geometry, it starts to reflect back. And if you wait long enough, basically wait for the travel time between the top of the ADS2 throat and the bottom for the wave to come back, then indeed it returns in some rather coherent echo, so not looking very black hole-like. And so at least in this approximation where you're just solving some supergravity wave equation, initially promising quasi-normal mode behavior turns into a not very black hole-like behavior because the geometry doesn't really have a horizon. And so, well, at this point, if you're, a fuzzball aficionado, you say, well, I took something that was too coherent and maybe more generic things will look more generic. But actually, the answer turns out to be a little more interesting. That if you look at this geometry and you look at what's happening to the probe as it goes down the ADS2 throat, as it gets to a point which is sort of the geometric mean of the two scales in the problem, A and B, the tidal forces get to be of order string scale or larger. And this is not because the geometry itself is significantly deviating from the BTZ geometry. It's simply because as the probe travels down the throat, it blue shifts. And so if you compute the tidal stresses that it experiences, they're a combination of the curvature and the velocity of the probe. And as the probe blue shifts, it overwhelms any small deviations of the geometry from the BTZ geometry. And this cap in the geometry does have some tails that extend up the throat, which are the multiple moments of the wiggly structure in the cap. And so that structure becomes visible to the probe as an increasing tidal stress that overwhelms it before it reaches the cap. And so what actually happens is in a more refined calculation where you do the calculation not in supergravity, but in perturbative string theory, then you find the analysis is very similar to a talk you guys heard from Hiroshi Iguri last summer, where you expand the geometry in some kind of Penrose approximation around the trajectory of the string probe. And you find that sort of, as I say, midway in a geometric mean sense down the throat, the tidal stresses start ripping the string apart. And so the kinetic energy of the probe as it's going down the throat starts getting converted into making a macroscopic string. And so by the time it gets to the cap, it's still relativistic, but it's macroscopic. And as it tries to turn around and climb back up the throat, it finds it doesn't have enough kinetic energy anymore because all that kinetic energy, much of the kinetic energy got turned into stretching energy of the string. And so the superstratum is a kind of a tar baby, to use a term from old folklore, that you throw something at it, no matter how hard you throw it, it never comes back. You'll notice that the return height is independent of the energy of the initial probe. So no matter how hard you throw it in, it gets stuck and it falls back down and basically thermalizes in the cap. Now, so it's black in that sense, that anything you throw in never comes back. But it's still, you can still, see this thing as it's wiggling around in the cap and thermalizing. It's emitting, gravitational radiation, et cetera, some of which may leak up out of the throat. And the scales for this, because the calculation we did here was in perturbative string theory, the thermalizations and other scales of this problem are string scales, not gravitational scales. But nevertheless, you see an indication of structure that's beginning to look black hole-like in a regime where we still have complete control over what's going on in the bulk. And to see, what's missing from this picture, my fervent belief is that we won't see what we're looking for in all details until we're able to count in the bulk for the full phase space of microstates and how one scrambles probes into it. So because in the superstrata, we don't have the full phase space of supergravity with all three charges, we shouldn't be expecting to see fully gravitational results for things like odd time order correlators or scrambling rates, et cetera. So to see what's missing, let's go back to the two-charge BPS states where we have a little bit more control. We have a complete enumeration of all the states. And let's see where the breakdown of our geometric and perturbative string theory intuitions start to take hold. And so let's go back to our wiggly supertube profile. And remember that it's in the duality frame we're interested in, namely NS5F1. It's some kind of this contour here is the location of a KK monopole core. And so we have a sort of a line of KK monopole structures. And so we haven't yet addressed the question of what happens when that wiggly contour tries to self-intersect. If it wiggles around and all of a sudden it starts touching itself, what happens? Well, so let's think about the KK monopole geometry. Here it is. Again, it's something that's governed, as all these things are, by harmonic functions. Now harmonic functions in 3 transverse dimensions. So basically there's a fibered circle in the geometry, and the harmonic function is such that as you get to the core of the KK monopole at x equals 0, in these coordinates, the size of the circle, the proper size of the circle shrinks away. And it shrinks away in a way that's completely smooth geometrically. So there's no, curvature defect at x equals 0. Okay. But if I have two such KK monopole cores, then this fibered circle grows from one core to some equator and then shrinks back in the other. And so there's a homological S2 in the geometry. And as as we go along the KK monopole core along its one-dimensional contour, these two cores, if they approach one another, this S2 starts to shrink and vanishes when the contour intersects. And so we should ask what happens, what can happen? Well, if we're in type 2b string theory, as we are as usual in the discussion of ADS3 CFT2 holography in string theory, we can wrap a D3 brane around this vanishing S2 at the intersection. And in fact, if you trace through the various dualities, it's just removing the Higgsing of a non-abelian W string of little string theory. And the remaining leg of the D3 brane is an effective string with a very light tension, which it's trapped to the 5 brane, which is or the KK monopole, which is the T dual of the 5 brane. And so it's trapped in the transfer space, but it can wiggle along the internal T4, which the 5 brane is still wrapping. And so this is, in this duality frame, the avatar of the little string. And so one gets a tensionless string when they intersect. The Hagedorn entropy of that tensionless string is the thing we expect to account for black hole entropy. So the thing we're missing by studying these 2-charge and 3-charge geometries is that we're in some sense in a Coulomb branch-like regime, if I could borrow the terminology of the phase diagram of branes, where the branes are somehow separated a little bit. So this angular momentum that I introduced as a sort of control parameter for the depth of the redshift in the geometry is not so innocent. It's something which sort of imparts an angular momentum barrier that keeps the branes apart a little bit. And so the less and less angular momentum there is carried by the branes, the more and more compact they are, the closer and closer they are to a self-intersection, but at the same time, the deeper and deeper the redshift is. So, so there's a sort of a phase transition that's going to go on where you un-Higgs these W strings, and at the same time, that's where you expect the horizon to start forming. Now I see I'm basically out of time. I have about 5 or so more slides. So I can go through about half of them, or I can.
I think we can go for 5 or 10 minutes. That's fine.
Okay.
That's
10 minutes.
okay.
Wrap up easily. Okay. So, so in these 2-charge solutions, one thing, because of the duality frame we're in, it turns and some nice symmetries of this particular sort of round supertube that is the starting point for many of these calculations. It turns out that a particular one of a class of those round supertube source shapes actually is a completely solvable in worldsheet string theory as a background. And so we found that if you just start with this collection of Kern algebra models and you gauge a particular U1 cross U1 subgroup, so you'll notice there are sort of 10 dimensions, 12 dimensions here, sort of 6 that you'd say are along the 5 branes and 6 more somehow. But if you gauge U1 cross U1, you eliminate 2 of them. And so this is a 10-dimensional target space geometry. And when you work through the details of it, it describes exactly a round supertube with the appropriate embedding. So I should say the appropriate embedding of the denominator group into the numerator group describes a round supertube, which has a parameter in the gauging discrete parameter K, which is related to the source configuration. Near the tip of the geometry is ADS3, and then rolls over at some point, governed by the radius of this Y circle to a linear dilaton. And all of this while having complete control over string perturbation theory to all orders in principle, because this is some exactly solvable worldsheet conformal field theory. This FZZ duality, which I was describing earlier, has some version in this background. And so it turns out that while the geometry has some Western-Witten model description, it also has a winding tachyon that lives near the tip that's described by a worldsheet superpotential, much in the way that the Euclidean 5-brane had. And that string condensate are the F1 strings that are bound to the 5-branes near the tip of the geometry. Okay, we can once again, look at what state we're describing in the CFT. We can enumerate all the vertex operators that implement transitions in the structure of this two-charge BPS state. And they're just ordinary vertex operators in the Western-Witten model. And in particular, you can identify what they are as perturbations of the superpotential. And they exactly correspond to what you would expect, that you can introduce some kind of wiggly shape into the superpotential with the appropriate twisted boundary condition, and see that the source of the 5-branes is coded in the structure of the superpotential. And so this phenomenon of FZZ duality is much more widespread than the context in which it was originally discovered. It's really a generic feature of this BPS configuration space. And so we can understand why something singular is going on when two 5-branes collide. Basically, the zeros of the 5-branes are the locations of the KK monopole cores, or the wiggly supertube profile. And so a collision of two 5-branes or KK monopole cores is a collision of two zeros of the superpotential. And so you can then look in a particular direction in field space and see that the sort of exponential barrier that the superpotential ordinarily provides from keeping strings out of the region of large X, which is the strong coupling region, that Liouville-like wall kind of goes away as you make the zeros of the superpotential collide. And so there's sort of like a long throat that develops in the geometry, which is the long throat of two 5-branes, and strings can get into that throat and reach strong coupling. And then you expect that the non-perturbative physics, like in other examples of like the matrix model of 2D string theory, where strong coupling physics is governed by D-branes, it's the same thing here. There are something which are akin to ZZ branes that are localized in this little throat that are governing the non-perturbative behavior. So there's a set of analogies with structures we know in other contexts, which make this picture of the sort of unhiggsing of little string theory the appropriate phenomenon to focus on. And I should say that the vertex operators that we have identified as telling you how to move along the half BPS configuration space have quarter BPS counterparts, and they correspond to superpotentials which preserve 0-4 supersymmetry instead of 4-4 supersymmetry. So work in progress is trying to explore that and see if the more general 3-charge solution space has similar singularities, and I fully expect so. And so this then leads to a sort of a general picture of what's happening as you start to move away from this, fuzzball. So it's a geometric fuzzball, which is entirely governed by supergravity, to fuzzballs where stringy ingredients are much more important and dominate the physics. So we can put a little bit more flesh on this by asking the following question. Can we somehow suppress the little string dynamics while keeping the geometrical picture? So I gave you a story about how when the little string physics becomes light, that the geometrical picture starts breaking down. You can ask the converse question, which is there a way we can keep the geometrical picture or the perturbative string picture while turning off the little string physics? And if we do so, what happens to the black hole regime? And so, so we can do that by replacing the T4 part of the compactification by either a T2 or by nothing at all. And you might say, well, am I not losing 10-dimensional string theory? And the answer is no, not really. That secretly what's going on is that the fibranes are turn out to be wrapping some slightly resolved conifold, where the scale of the resolution is so tiny that perturbative strings can't see it. But nevertheless, it's a situation which can be described by perturbative string theory in what's sort of called a non-critical type 2 string theory. And you can preserve supersymmetry by, there's still a chiral GSO projection, and all the things you're used to in critical type 2 string theory have versions. But by eliminating the T4 completely, you eliminate the space in which the wiggles of the little string were giving you lots of entropy. So it turns out that that by eliminating the T4 entirely, the linear dilaton throat and the ADS3 cap it ends in become completely stringy, and you're on the correspondence side of the phase. You're on the stringy side of the correspondence transition. And so it was argued by these gentlemen that when you're on that side of the correspondence transition, the BTZ black hole states are not normalizable. And so the Hilbert space just contains perturbative strings. So, correlation is not causality, but I think it's intriguing that at the same time you eliminate the wiggles that cause the little string to dominate the entropy, is the same time that the black holes disappear from the spectrum, and then the high energy density of states is completely accounted for by the Hagedorn entry of perturbative strings rather than little strings. So I think that contains a lesson perhaps more generally that we should be careful to check what side of the correspondence transition we're working on in a particular situation. And so, for instance, if you do a calculation in the symmetric orbifold CFT, that's at the correspondence point. The ADS3 radius of curvature is the string scale. The C=1 matrix model of non-critical string theory has no black hole states. Basically, for this reason, the slope of the linear dilaton is too large for there to be normalizable black hole states. And I suspect the same thing is true for vector models and perhaps even for SYK, which again has it doesn't have a full stringy towers of states, but it has a sort of a leading Reggie trajectory worth of light states of higher spin modes. And you could wonder whether the physics you're seeing there is non-local enough that it could explain what's being seen without having black hole horizons. So just to summarize, we see that we can find oodles of geometries that are separated from the black hole region by a phase transition, which in this context is sort of the appearance in this context of something we've been familiar with for a long time in other examples of gauge gravity duality. That is, if you're in the correspondence regime weak coupling, the regime that has the black hole entropy of states is kind of a deconfined regime of the non-abelian brane degrees of freedom. And in supergravity, those degrees of freedom are, when there's no horizon, those degrees of freedom are in some sense confined or Higgsed because the cap geometry is in some kind of Coulomb phase. But when the horizon is wanting to form, those degrees of freedom sort of unhiggs and become the light actors in gravitational entropy of black holes. And we're now starting to see this structure on the gravity side of the duality, not just in the weak coupling gauge theory, at least in these particular examples. And I've argued that these degrees of freedom are the entropic degrees of freedom of the black hole. And when they're absent, the black hole states are absent. And I also tried to argue that the correspondence transition might be a useful probe of the process of horizon development. And let me just close with one last thought, which is the horizon seen this way the phase boundary? And if it is a phase boundary, by analytically continuing the regime outside the horizon, are we making the mistake of analytically continuing a phase across a phase transition where it no longer applies? So with that thought, I'll conclude and thank you for your attention.
Okay, thanks, Emil. Maybe we can all unmute and thank the speaker.
And my apologies for running over.
No worries. Okay, the floor is open for questions. Yeah, maybe I can, Emil, you mentioned in passing that some heavy light or heavy light correlators were computed. Do they fall into the expectations of ETH here or no? I guess not.
So
could you tell us?
3-point functions are BPS.
Mm-hmm.
And so so the expectation values of light operators in the heavy backgrounds of these supertubes and superstrata are just conform to what you would expect on the basis of supersymmetry. And in fact, they're used to identify what CFT state you have by looking at the expectation values of light probes in the presence of this heavy background. Now, if you ask for like 2-point functions in the heavy background, so asking about some probe, that's intrinsically not BPS. And so there are a number of calculations by many of them by Giusto and Russo and collaborators, where they computed both in the perturbative CFT, the symmetric product, and in supergravity, and they observed a mismatch between the probe behavior and the behavior in the geometry. And in the hindsight of this work that showing that very stringy things happen when you get far down the throat, that shouldn't be surprising that things in the perturbative CFT dramatically differ from what you see in the geometry, because stringy effects can happen, and it becomes important that there's a big gap in the spectrum as to what you see, and so what you see doesn't remain constant as you dial between weak and strong coupling.
Okay.
Let me ask a question, Emil. This is Steve Schenker.
Mm-hmm.
Could you just, I mean, it's sort of a invitation. Could you elaborate on this last point in your summary? I guess it went a little fast for me. So we're talking about the deconfined phase of these W strings, or these strings in the little string theory.
Mm-hmm.
And now, in a region where you have a geometric horizon, I don't know, the analog of large additive coupling, or in ADS5, is that deconfined transition under control? Is like, is it, can you like, it's not like a weakly coupled gauge theory.
It's not like a weakly, so it's, in the place where I introduced it, where you're wrapping D3 branes,
Yes.
around some vanishing cycle,
Yes.
what you're saying is that a string made out of D branes is
Yes.
as lighter than fundamental strings.
Right.
So by definition, you're losing control over the
right. So, but I mean, do you might expect, like our experience in ADS5 process 5 is that the quote unquote deconfinement transition becomes, or what was the Hagedorn transition becomes the Hawking-Page transition.
Right.
And so, I mean, which is usually strongly first order.
Right.
So are you imagining that the transition you're at the horizon would be a strongly first order kind of thing?
Yeah, if it's really is a question of, is there any kind of geometrical picture of the degrees of freedom responsible for, I should let me back up a step. Is there any sense in which geometry applies to the interior? So the fuzzball paradigm says that there's structure out to the horizon.
Right.
And so the answer to what happens to these little strings is that there's going to be some manifestation of them at the horizon scale in order to solve the black hole information problem. Now, if there's a sense in which there's a geometrical picture of the interior and it's somehow an infalling probe, sees a geometrical interior, it would have to be that there's some kind of sequestration of the probe's dynamics from this, huge part of the phase space
Right.
governing the entropy. And, Matur has had some speculations along those lines, something he calls fuzzball complementarity.
Right.
There's a disparity between, things whose radial momentum is large, seeing something which looks approximately geometrical, versus things whose radial momentum is small, feeling strongly kicks that it's getting from little strings. And so, different probes see different things, and maybe infalling probes can be rescued as seeing something that's approximately geometrical, even if there's structure there. But that's really a question of what is the ultimate fate of these, stringy degrees of freedom in the strongly coupled regime.
I mean, do pictures like that have anything to say about why the Euclidean black hole horizon gives the right entropy, the Gibbons Hawking calculation? I mean,
so the Euclidean calculations, they don't really care about what's. I mean, there is no black hole interior in those calculations. So.
Right, but you might think in a fuzzball description there should be no alternative but just to count microstates or something. I mean, why are you allowed to use the horizon to get the entropy?
So that's a question of is there, what's the status of effective field theory for doing computations? So for instance, even in this black 5 brane, there is a stringy correction to the horizon, right? There's this string condensate that's living near the Euclidean horizon, but it makes subleading corrections to the black 5 brane thermodynamics. Doesn't vitiate your Bekenstein Hawking calculation of the entropy of black 5 branes. Things like temperature of Hawking radiation, that's related to the acceleration of constant R trajectories and so on. So until you get to the order of the stretched horizon, none of that gets changed either. the surface gravity calculations, I think.
Okay, so you're what you're telling me is you should make it's an effective field theory will be smart enough to be able to compute this this large contribution to the entropy. There will be a term in the effective field theory that will know about all this microscopic phase space.
Right, and much of that has to do with the fact that what's emerging is diffeomorphism invariance. Right, I mean, the idea that black hole entropy is another charge of some emergent diffeomorphism symmetry, going back to Wald's ideas.
Okay, but I mean, the fact that it precisely agrees with the microscopic phase space count seems miraculous, but all right, I'll have to think about that. Thanks. I'll stop now. Somebody else probably has a question.
So a few slides ago, you had this three inequalities. One was the microstates that had the NP to the 1/4 entropy. And yeah, right there, like this last line here.
Mm-hmm.
So what you described were the second thing, right? The stringy microstate solutions.
So
after that.
So virtually all the work that's been done is constructing things within the supergravity approximation, where geometry applies everywhere.
Mm-hmm.
And I skipped over it, but because I was running out of time, the reason I like this FZZ duality is that it enables us to get a picture of the near source structure of more general things where there's sort of like 0-4 deformations of the world sheet theory can include things where, you know, their vertex operator description in this around this solvable point have, you know, more general left moving dependence than what you would get in supergravity. They would be, you know, realistically string condensates near the horizon. And so, you know, a naive counting of those is that there are many more of those just because the left moving oscillator dependence can be more arbitrary than this sort of zero mode structure of supergravity. And so there are definitely more of those, but then I suspect that even that will not be enough to account for extremal entropy because of this phenomenon that, you know, when the underlying supertube profile starts to self-intersect, there are strong coupling phenomena that are outside of perturbative string theory.
But you believe that after you include, you know, the self-intersections correctly, after you account for all the dynamics there correctly, that is the generic fuzzball that you wrote here.
Yes.
Okay.
Yeah. And of course the issue is that you know, how do we? I mean, the problem now becomes as difficult as finding the solution to little string theory, right? I'm basically arguing that all this ADS3 physics is a kind of a particular crazy limit of little string theory where you compactify it on a 5 torus, make one cycle of the 5 torus enormous, and make the winding charge along that circle large. And even in that limit, you know, I'm claiming that little string physics still comes back to bite you in the regime where a horizon is starting to form in the deepest parts of the geometry.
Okay, thanks.
And by the way, then you know, intuitions that you have from the corner of the moduli space where n5 equals 1 in the effective description are somewhat misleading, because if you have only one 5 brane traveling some trajectory, it can't self-intersect because it's some chiral profile. So all of this physics I'm describing applies for corners of the moduli space where there are two or more 5 branes in the effective description. So there's certain aspects of you know, truly black hole physics, which are not well captured by the symmetric orbifold.
Okay, thanks. Maybe final questions for Emil?
Well, I can make one comment that's might be an interesting thing to do. It turns out when you compute an OTOC and you go up to 50% of the scrambling time or something, the shock wave that you might use to calculate that in gravity turns out to be very close to the horizon. It actually is much closer than the Planck length. It's dimension dependent, but in dimensions 4 and greater, it's not given by the Planck length scale. It's given by the scale where where the strength of shockwave scattering is strong, where G Newton times mental stem S is order 1 or something. And that turns out to be larger than smaller than the Planck length parametrically. And so I wonder if when you sort of expect to, of course, you don't control situations where, horizons are there and the stuff you want, but would you predict a deviation, or would one predict or guess a deviation in such things that the OTOC, which is an outside the horizon thing at, long, but for us, not very long times, would show a deviation?
That's an interesting question. And I one thing that's been on my to-do list to think about, which may start getting at that question, is, as I described, this round supertube has a limit where it approaches an extremal black hole. But on the other hand, the perturbative string theory is under a significant degree of control. So I don't know how doable a 4-point function would be in that background. I mean, it's some 4-point function in SL2 Weston-Witten models and so on. If that 4-point function was doable, one might be able to take the sort of limit you're interested in and ask what's going on.
Yeah, okay. I worry about those systems may not thermalize and might not have what you want, but.
Yeah, so I mean, there are other, so there are related issues which are associated with the fact that as you go towards extremality, the scrambling time lengthens. And so that's, a curse, but maybe also a bonus. You have a long time to to look at things before they go haywire. But there is a prediction in supergravity about what happens to scrambling as you go towards extremality. It doesn't go away. It just gets long. Question is whether the timescales are so long that there would be some expectation for you to lose control with a perturbative string calculation. But for me, the utility of this program as it stands now is that it can get you close to the regime where there's a horizon without there being a horizon. So you can study, what new degrees of freedom are you engaging that you didn't know about in gravity in a controlled way. So the sorts of questions that one's interested in, when there actually is a horizon, are probably beyond reach. But what you expect to be black holes to be made of in a completely bulk description seems to be closer than just saying, oh, there's a Hawking-Page transition, Um, um,
I mean, along those lines, what is your view of the question of whether you should include both the black hole and the fuzzball states? Like, suppose we have enough of these 3 charge configurations eventually to get the full square root n1, n5, np. Should we also include the black hole?
So I think these are, so if you really had control over complete, bulk string theory, I think you'd probably say that these are subleading saddle points in a complete path integral.
But aren't there like enough of them somehow that you get the, I thought, maybe I misunderstood. I thought that the,
so you would need the third charge to go like square root of np, and it only goes like np to the 1/4. So you're sort of parametrically way far away from having enough states. So there's no, as far as I know, at the moment, there's no contradiction. Because
sorry, I think I must have misunderstood. I thought that
outliers.
After properly accounting for the self-intersections, you thought that maybe you could get all of the.
Oh no, I would say what happens is that when the self-intersections start forming, you just lose complete control over the bulk picture at the moment.
I see. Okay. But then, so then the ultimate picture would be that the black hole would still describe most of the states, and that the fuzzballs would describe a small fraction.
Yeah. So here's where I have a little bit of a quibble with the. There's sort of a conflation that goes on. People think that fuzzballs are these geometrical solutions. Rather, I would say that the fuzzball is just a sort of like a general picture that the black hole is some kind of brane bound state, and that it has structure on horizon scales. The things that are studied are for the most part what are called microstate geometries. So they're things for which the supergravity approximation applies. And so the things that are kind of smooth and horizonless within supergravity are very specially finely tuned coherent states that live within the ensemble, the generic element of which is something which looks to a low energy observer like it has a horizon. And the deep question is whether all of these structures that you find in these geometrical solutions have any bearing on what the generic state looks like, or whether it's some red herring. And to my mind, it's sort of like these are some kind of portal where you can find these nice finely tuned coherent states that carry all 3 charges, that live within the part of the phase diagram. I didn't mention this, but you can be in the part of the phase diagram where when you turn on this third charge, you're up here, and yet there's no horizon. Okay. So these 3 charge superstrata can live up here, and yet have no horizon. And so they sort of get you within the part of the phase diagram that you want to be in without being a generic state. And then the question becomes, okay, if you kick it a little bit, presumably it becomes a generic state by some kind of thermalization process. And so it's sort of like, it gets you to the neighborhood you want to study while still having control over all the low energy physics. And then the question is, okay, once you perturb it a little bit, where does it go and what happens, and what stringy things happen? So to me, that's the utility of this panoply of solutions that has been the subject of study for many years now, is that it sort of gets you in the neighborhood of the thing you want to study without actually being the thing you want to study.
I guess maybe one could then ask the question, let's say you take the stringy stuff, which has structure at the horizon. There's not a metric, it's not supergravity, but some stringy stuff that has structure at the horizon. And you find enough of them to account for the full entropy. Then do you still have to add the black hole? To the,
No, because the black hole was some kind of low energy approximation. It's sort of, the black hole was a kind of a Wilsonian error that you tried to integrate out things and just work in the effective supergravity theory, but not realizing that there were degrees of freedom that are just as light as the supergravity degrees of freedom that start being that light at the horizon scale.
so you would say you just keep the stringy things and don't keep the black hole, like
Yeah,
these stringy.
but those stringy things, you would expect only to arise within, to arise at the what people call the stretched horizon. Stringy things start happening at string scale outside the horizon, and little stringy things start happening Planck distance from the horizon. And that integrating those things out was just making a mistake.
Okay. Okay. Any more final questions? Okay, if not, let's thank Emil again. Thanks, Emil.
Thank you.
Yeah.
Yeah. Thank